Welcome, ladies and gentlemen, to the free response question review. In today's video, we will be covering the 2012 Calculus BC exam. Question number 4 is a typical table style problem with a BC twist to it. We're given a function that is twice differentiable with x being greater than 0, with f of 1 being 15 and f double prime of 1 being 20. Values of f prime, the derivative of f, are given for selected values of x in the table above. So let's start answering some of these questions. Part A, pretty basic AB style question here. They're asking us to write the equation of a tangent line at x equals 1, and then we'll do some linear approximation. So hopefully this is pretty much second nature to you by now. But if I'm going to write the equation of f at x equals 1, I better identify that f of 1 is equal to 15. So f of 1 is equal to 15, so that allows me to say that y minus 15 is equal to some type of x minus 1. And then from here I can go and just identify what the slope is. Well, what is the slope at x equals 1? Well, that's going to be right here. That's going to be this piece of information right here. And I'll go and get rid of it because I might need to see it more clearly in a little bit, but I just throw it out an 8. And then half the problem is already done. So from here, it's telling me now to approximate f of 1.4 using this line. So how do I do that? Y minus 15 is equal to 8 times 1.4 minus 1. That's going to be 8 times 0.4 plus 15 is equal to y. And at this point, you can actually stop from here if you didn't want to go any further. You could have actually just added the 15 over. But because the video, I'll go ahead and just simplify it. So 8 times 4 over 10 plus 15. Those guys are going to somewhat cancel, giving me a 4 up here and a 5 down here. So that gets me 16 over 5 plus 75 over 5 for a common denominator. And I end up getting 91 over 5 as the linear approximation for A. Okay, let's go and move on to part B. Part B says use a midpoint Riemann sum with two subintervals of length and values from the table to approximate the integral from 1 to 1.4 of f prime of x dx. And then we will use this approximation to estimate the value of 1.4 and show the computations that lead to the answer. So I think what this problem is trying to get us to do here is it's trying to get us to find multiple ways of solving for f of 1.4 and seeing how they're all a little bit different from each other. So let's go ahead and do this midpoint Riemann sum here. So I'm going to trust that you have the table in front of you here, so I'll just go and integrate without having to scroll up and down and up and down. And so from here, let's go and just graph this thing. From here, I've got my 1, which is going to be at 8, 1.1, which is going to be at 10, 1.2 is going to be at 12, 1.3 will be at 13, and 1.4 will be at 14.5. Because this is a midpoint sum, I will be taking my heights from the middles of the rectangles, so that should be relatively easy to do. I'll just go ahead and add up the darkened parts of my height, things that are in dark yellow. And so what this gets me is it gets me a base length of 0.2 with a height of 10, and then another base length of 0.2 with a height of 13. Now I'll go and simplify it. That's going to be 0.2 times 23, which is going to be 23 over 5. So that is the approximation of this Riemann sum right here. So how do I use this information? Well, remember, they're asking me to now figure out the value of f of 1.4 using this estimation, this 23 over 5. So how do I do that? Well, that's going to go back to our old buddy, the first fundamental theorem of calculus. That's going to be the integral from 1 to 1.4 of f prime of x dx equaling, and in fact I should probably change colors for this, that's going to be f of 1.4 minus f of 1. Well, we already know what f of 1 is. He's 15. which means f of 1.4 is going to equal 15 plus the integral from 1 to 1.4 of f prime of x dx. We determined him a few seconds ago to become 23 over 5. And we know that 15 is 75 over 5 on common denominator. So we can go and add this up. And what we get is 98 over 5. So a little bit more than our linear approximation, but it's okay. Remember, we're looking at different ways of getting the same answer, and they're all approximations, so they're all going to deviate from each other just a little bit. All right, let's see if I can't scroll down here a little bit more. In fact, I'm running out of space, so I think I'm going to delete some of this stuff, and then I will go ahead and move on to part C. Part C is asking us to use Euler's method starting at x equals 1 of 2 steps of equal size to approximate f of 1.4. So here we go again. We're approximating f of 1.4 in a slightly different kind of way. So if we're going to show the computations that lead to the answer, we have to figure out and remember, how do we find the new y value of Euler's method? And if you want, you can pause and say, yep, I know how to find the new y of Euler's method, and I would write that down immediately. So I would say the new y is equal to m, which is dy over dx, the slope, times the delta x, which is the change in x at that moment in time, plus the old y, and that's how you get the new y. So I would make our table. So I got an x, a y, dy over dx, or m in this case, and then new y. So as we're starting at 1, and we're going to end at 1.4 with 2 steps of equal size, that means that my change in x is going to be 0.2. So let's go and figure out what some of these values are. Well, what's f of 1? Well, f of 1 is 15. And then dy dx, according to our table at that moment in time, and again, I encourage you to look at the table for this, your dy dx at x equals 1 is 8. And then you plug that stuff in. So you get 8 times 0.2 plus 15. So in the interest of saving time, you end up getting 83 over 5. Now I know it's a pretty nasty looking number, but it's okay. It'll clean up at the end of the problem here. Dy over dx at that moment in time of this 83 over 5, and again I have to remind you, 83 over 5 is the result of the new y. So the new y goes into the y of the 1.2. And so dy dx at this moment in time, again, I encourage you, please look at the table to find out what that is. F prime at 1.2, the table actually explicitly calls it 12. So we find new y again. So 12 times 0.2 plus 83 over 5. After a bunch of common denominator hocus pocus, you get 95 over 5, which you can leave the same way, or you can call him straight up 19. So please, under no circumstances, do not go here, do not go here. If you solve for this x right here, you are finding f of 1.6. You don't want that. We don't want that. We want f of 1.4. So from here, we just write down f of 1.4 is approximately equal to 19. And we close up shop on that problem right there. All right. Let's take a look at D. D is probably one of the most obscure parts of this thing. It says write a second degree Taylor polynomial for f about x equals 1, and then use the Taylor polynomial to approximate f of 1.4. So this is actually our first real exposure to a Taylor series inside of an FRQ. So let's go ahead and see what this thing is going to end up becoming. Well, remember, a Taylor series is really just f of a plus f prime of a times x minus a plus f double prime of a times x minus a squared over 2 factorial plus dot dot dot. Well, in the case of this example, a is 1. They told us that, which means our generalized t of x Taylor polynomial will be f of not a anymore, but f of 1, plus not f prime of a, but f prime of 1, times x minus not a, but 1. And then plus f double prime of 1 times x minus 1 squared over 2 factorial. Now, how do I know when to stop? Well, that comes down to how they asked the question. Notice, they said they want a second degree Taylor polynomial, which means the highest power that they want to see from me is none other than the power of 2. So after this, I'm almost there. So what am I going to do with this information? Well, from here, I know that f of 1 is 15. The problem told me that at the beginning. Plus, I know that f prime of 1 is 8. They told me that as well. Well, that's going to be times x minus 1. Plus, f double prime of 1, well, I believe they told me that too. That's 20. They said that right over here, in case you're forgetting where that came from. That information came from here. They told us. And then that's going to be times x minus 1 squared over 2 factorial. And that's t of x so far. Well, here's the thing. This is the Taylor approximation anywhere on the function. But in this case, we don't want the approximation anywhere. We want the Taylor polynomial of 1.4. So that's going to be 15 plus 8 times 1.4 minus 1 plus 20 times 1.4 minus 1 squared over 2 factorial. So what you get is you get 15 plus 8 times 0.4 plus 20 times 0.4 squared over 2 factorial. And after a bunch of hocus pocus on the algebra, you will then get 495 over 25. Now, again, it's important to note you actually could have stopped the problem right here. You could have stopped it right here and gotten full credit. In fact, on the day of the AP exam where you're crunched for time, I would encourage you to stop right there. But just because we have the time in the video, I figured I'd just simplify it as best I could for you. Yeah, I think that will wrap it up for this particular free response question. It's not totally threatening, but it is different. So please make sure you're paying attention to how I did these sections here. If you have any questions, please leave them in the comments. I will address them as soon as I can, and we will see you in the next video.